Ever wondered how chemists crack a chemical mystery? You know, when you mix two things together and they form something totally new, how do you figure out the exact recipe for that new substance? Well, today, we're going to crack that code. So, what is the secret recipe? When we mix two chemicals, how do we know if they're combining in a simple 1-to-1 ratio? Or maybe something more complex, like 1-to-2 or even 1-to-3? Finding this ratio, what scientists call stoichiometry, is the key to the whole puzzle.
Okay, let's dive right in. For our investigation, we've got two main ingredients. We'll just call them species P and species X. When you mix them, they react and form a new chemical complex. But is that new complex PX, or PX2, or maybe even PX3? That's the question we're here to answer.
And that right there is the core of the problem. We need to find that exact combining ratio. Is it one molecule of P for every single one of X? Or does it take, say, 2 molecules of X to tango with 1 of P? Getting this right is absolutely fundamental.
Luckily for us, chemists have this brilliant detective tool up their sleeves. Its official name is the method of continuous variation, but pretty much everyone knows it as a Jobs plot. It's a really clever technique designed for this exact kind of puzzle.
You know, the principle behind it is actually beautifully simple. Imagine you're trying to find the perfect recipe for a new drink. What would you do? You'd mix your two ingredients in every possible ratio, right? A little bit of this, a lot of that, then a bit more of this, a little less of that, all while keeping the total size of the drink the same. Then you just find the one that gives you the strongest result, in that case, the best taste. Well, a Jobs plot does the exact same thing, just with chemicals.
So, how does this detective actually get to work? Let's get into the nitty-gritty of the investigation. The very first thing we have to do is prepare a whole series of mixtures, each one with a super specific and carefully controlled ratio of our two ingredients. This setup here is absolutely crucial. First, we make solutions of our two ingredients, P and X, and we make sure they are at the exact same concentration. Then we start mixing them together in different volumes. But here's the really clever part. We do it in such a way that the total amount of stuff, P plus X, in every single test tube stays perfectly constant.
Now take a look at this. You can see just how systematic this whole process is. We prepare a whole lineup of solutions. We start with a mixture that's almost all species X, like 9 parts X to just 1 part P. Then we just gradually walk it back, decreasing X and increasing P, all the way down to 1 part X and 9 parts P. We're literally testing the entire spectrum of possibilities.
Okay, so we have all our mixtures lined up, but how in the world do we figure out which one created the most of our new complex? Well, the clue comes from light. We're going to measure something called absorbance.
Absorbance is pretty much what it sounds like. It's a measure of how much light gets soaked up when you shine it through a solution. See, in our case, the new complex we've made, our product, just happens to absorb light. So it stands to reason, the more of that complex you have in your test tube, the more light it's going to absorb.
So here's the bottom line. The crucial point, the one mixture that has the highest amount of our new product is going to absorb the most light. It's going to give us the biggest, strongest signal. And that signal, well, that's our smoking gun.
And now, for the moment we've been waiting for, the big reveal. We've collected all our data. We have an absorbance measurement for every single one of our mixtures. It is time to plot this on a graph and let it show us the hidden answer. So we're going to plot our absorbance signal on the vertical axis against something called the mole fraction of species X on the horizontal axis. That mole fraction is just a way of representing the ratio of X in each mixture. So when we do this, what do you think the data is going to tell us?
And there it is. A peak appears. The graph isn't some random scatter of points, and it's not a straight line. It rises up to a maximum and then falls back down. That peak, the point of maximum absorbance, it tells us everything. It marks the exact mixture, the sweet spot where we formed the most product.
And in our example, that peak happens right here, at an x-axis value of 0.667.
Now that number, 0.667, isn't just some random point on a chart. It is the mole fraction of X in that perfect optimal mixture. It is the key that unlocks the entire secret recipe.
And this is where the magic happens. A mole fraction of 0.667, well, that's just a fancy way of saying 2/3, right? It means that in our perfect ratio, 2/3 of the molecules are species X, and the other 1/3 are species P. So the recipe is 2 parts X for every 1 part P. The secret formula for our complex is PX2. Mystery solved.
Now, of course, like any good piece of detective work, you've got to follow the rules of the game. To make sure our results are solid and that we're not just chasing a false lead, there are a few important precautions to take.
Yeah, to make sure the results are legit, chemists follow a few key rules. First, they check that more light being absorbed really does mean there's more complex, a nice consistent relationship. Second, they've got to control other things like the pH just to make sure nothing else is interfering. Third, they double-check their work at different wavelengths, kind of like using different colored lights. The peak should pop up in the exact same spot every time. And finally, if they repeat the whole thing with different starting concentrations, they should get the exact same recipe. It's all about confirming the answer is real.
So the Jobs plot is just an incredibly powerful way to reveal the hidden recipe of a chemical complex. It really makes you wonder, doesn't it? What other invisible patterns or perfect ratios out there in science or, even in life, could we uncover just by systematically changing the mix and looking for that peak?